This is the steady state of the logistic map. I'm sure a few of you guys have heard about the logistic map from Veritasium's YouTube video on it, link in the description. While his video is an excellent source for an introduction and gives really great motivations behind the logistic map and some really cool features of it, he didn't really go into the deep mathematics behind it. So I figured I'd make this video on it. One of the cool things about chaos theory is how intertwined it is with numerical simulations. So it's pretty natural to start with a simulation. In the following, I have a grid with many starting points. I then iterate each one of these starting points, each of the points on the grid, many times until the final quote-unquote steady state of the logistic map is reached. I think this iteration is pretty beautiful, so I'll show how these initial states go through a transient state and finally arrive at their quote-unquote, again, steady state. Keep this animation in the back of your mind because I'll be referring back to it for the rest of the video. Now, let us unravel some of the math behind the logistic map. There are many mathematical phenomena that appear in the logistic map, but I can only go over so many in this video. So in this video, I'll be going over a few of the foundational concepts. So that includes bounds. So how did we figure out our bounds for creating the logistic map? I'll be going over what are stable and unstable points, along with what are orbits. I'll be going over the mathematical concept of bifurcations. I'll go over how we can predict what kind of bifurcation is going to occur. I'll be going over a quick intro to Sharkovskii's theorem. So this is kind of an advanced topic, and I almost put it as like a bonus just to show you how deep this mathematics gets. And then similarly, I'll also do a quick intro to Lyapunov exponents. All right, so the first kind of most natural, lowest level thing that you need to find is bounds. So why did I choose r equals 0 to 4 and x equals 0 to 1, or element of 0 to 1, for my model? Well, the x is supposed to usually represent a population percentage, where x equal 1 means that the population is the lowest such that xn plus 1 will equal 0. So that's just like you're maxing out the environment for 1 year, you're completely destroying it, and the next generation completely dies off. And then obviously x equals 0, your population is kind of dead. And then obviously you can't have a negative population. Okay, so then the real question is, why is r an element from 0 to 4? So r is supposed to represent a breeding rate or a reproduction rate. So it doesn't make sense to be negative. So must be greater than or equal to 0. Okay, so that makes sense for our lower bound. So why is our upper bound equal to 4? Well, consider some initial population xi that is also an ideal initial population. So xi such that after one mapping, so one function of xi, which is equal to r xi 1 minus xi, which is going to be defined as x2, such that x2 is greater than or equal to xn for all n greater than or equal to 2. So basically it says that this second iteration, so after my initial or ideal starting point, my second iteration is for sure going to be the highest. So this is just a maximization problem of this function, right? So all we have to do is find what xi is. So we just say f prime of x, right? We can solve a maximization problem. It's just from calculus 1. So it's going to be r 1 minus 2x. So then in order to find a maximization, we just set it to 0. So we can divide by the r, so we just kind of get rid of that. So then we're left with 1 equals 2x, which then goes to x initial equals 1/2. Okay, so if x initial equals 1/2, that would mean x2 is equal to r times 1/2 times 1 minus 1/2, which is equal to r times 1/4, and it has to be at most 1, right? My highest population size that I can get has to be 1. If it's not 1, then my population size will go negative, and I don't want that. So then we get r equals 4 for our upper bound. Alright, so now that we know the bounds, which is kind of making sure that we know our bounding box of our function, right? So that's right here. So we know that this is 4, we know that this is 0, we know that this is a max of 1. Okay, so now how do we start describing these lines here, here, and this bifurcation here? So the way that you start to understand this is the concept of a steady state. So a steady state is just any point, any value of x that is mapped back to itself. So some point is mapped and gets pointed directly back at itself. So how can you write this down in an equation? Well, that just means f of x, whatever our mapping is, must go back to whatever x started out with. Okay, well this is easy for the logistic map. It's just r, x, 1 minus x. And then we can solve this because it's just a quadratic, right? We're trying to solve for x in terms of r, right? Because r is just a variable we can change. So we get xr, 1 minus x must equal 0, which then goes to x r 1 minus x minus 1 must equal 0, which is, again, pretty easy to solve. We get x equals 0, so let's call this steady state 1. And then we also have x steady state 2, which then is going to be the r 1 minus x minus 1 equals 0, which then solves to 1 minus x equals 1 over r, then goes to x equal 1 minus 1 over r, which is also the same as r minus 1 all over r. We'll call this x steady state 2. Okay, cool. So now we know all the steady states that map back to themselves, and now we just have to figure out, are they stable or unstable? Basically, if I start at 0.001, am I going to go to 0, or am I going to go to somewhere else? Okay, so how do we figure this out? Well, we have to look at the derivative of our map. So if our derivative is less in magnitude than 1, our point is stable. So why is this? So the way that I kind of internalized this and memorized it almost is just thinking, if I'm a little bit off from this point and my power is 0. Basically it's lambda to the n is how you can approximate how points are going to move by your steady state. If this lambda is in absolute value less than or equal to 1, then these are going to collapse down onto the steady state, right? Because 0.999 to the 100 is basically about equal to 0. So the difference is pretty much going to go to 0, and we're going to fall to our steady state. That's kind of how I just memorized it, but this is the most important point. If the absolute value of it is less than or equal to 1, it's a stable point. And then, obviously, f prime of x greater than 1 leaves to unstable. also called repelling. Cool. So let's check out our steady states S1 and S2 to see if they're repelling or if they're stable, attracting. So let's start with f prime of x steady state 1, which is equal to 0. So that's going to be, from above, we have that our derivative is right here, r, 1 minus 2x, which then goes to r. So we have f prime x steady state 1 is equal to r. So if r, an absolute value, is less than or equal to 1, x steady state 1 is stable. Cool, and that is exactly what we see in our figure right here. From 0 to 1, our x steady state 1 is stable. And then after that, it's actually not stable, right? Because there's no value down here. It just turns blank. Okay, so I'm going to take a second break in the video, and what would you guys guess that the equation of this curve is? So the equation for this curve is going to be our x steady state 2, which equals r minus 1 all over r. Yay, happy. But let's go back and quickly prove this. So we have x prime x steady state 2 is equal to r minus 1 all over r, which is equal to r 1 minus 2 r minus 1 over r. Okay, so we see that this is a r minus 2 r minus 1, which equals r minus 2 plus 2, which equals r minus 2r plus 2, which equals minus r plus 2. So in order for this, an absolute value, to be less than or equal to 1, our lower bound is going to be r equals 1, right? At 1, this is going to be 2 minus 1, which equals 1. And then obviously in absolute value, that's a less than or equal to 1. And then for our upper bound is going to be r equals 3, right? Because negative 3 plus 2 equals negative 1 in absolute value, which equals 1. Yay! So we're assuming from r equals 1 to r equals 3, x steady state 2 is actually stable. So if we look at our curve, we have from r equals 1 to r equals 3, our steady state is r minus 1 all over r, which is awesome. So now a really cool thing happens. So this is called a bifurcation, specifically a pitchfork bifurcation. What a pitchfork bifurcation means is that it's just splitting in two, and then the steady state, so x steady state 2, still continues on, but it's actually unstable. So the points will iterate along it further and further away until it reaches our steady state of period 2. So what does a period 2 mean? Or how do I know that this is a period 2 orbit? Well, that's because this is plotting a steady state. This whole map is. And then since it's plotting a steady state and there's 2 points right there, that means that the map is just iterating back and forth between 2 points. It's switching back and forth between 2 points. So how do we figure that out? So how do we know when this next bifurcation is, right along this line right here? How do we know what this point is? Well, we can figure that out because we just need to figure out where it bifurcates. So what is a period 2 orbit? Or what does that mean? How do we write that down? So that's just going to be f of x, right? So we're just iterating our map twice, and then that's going to have to go back to our original x. So we have this point and this point that just iterate back and forth through each other. Cool. Okay. So what is f of x? Well, equal to question mark. Well, that's equal to f of x, which is rx, 1 minus x. And now everywhere we see an x in my f of x, we just substitute it with this part right here. So we have rx, 1 minus x, times the group 1 minus rx, 1 minus x. And there's my big. Cool. So now expanding this on Wolfram alpha, we get right here f of x equals this monstrosity quartic. The cool thing is we can still solve this. So since it's a quartic, that means that we can still solve it. Actually, even analytically, there's a quartic equation from group theory. If we get into a quintic, the fifth root or the power 5 polynomials don't have any solutions. But that's kind of in a group theory. But yeah, that's another cool topic. But anyway, we know how to solve this. So we know that our x steady state 1 is going to still be present, which is 0. We know that our second steady state is also still going to be present, because if you iterate a steady state just another time, it's obviously going to stay 0. So it's f of 0 is again 0, which is f of 0, which is 0 again. Likewise, our x steady state 2 is also going to be a root of this. So r minus 1 all over r is again a root of this quartic polynomial. And then to find the other two, I actually, again, just plugged it into Wolfram alpha. And the solution that we get from Wolfram alpha is x of period 2 points is actually r plus 1 plus or minus root r squared minus 2r minus 3 all over 2r. Whew, that's hard. So let's check what happens to this period 2 orbit to see if it's stable or unstable. So we check f prime of our iteration. So we say, let's call f of x is equal to, or defined as f of x. So then f prime of x is equal to this. So you can check for yourselves. And then again, we just check f prime of x of period 2 points. Let's consider the plus 1. And that is just equal to this. So this, again, was done on Wolfram alpha because, again, if you're using a computer to do simulations, you might as well use a computer to do pretty simple algebra tricks that are just going to be tedious to solve. So this is our steady state. Okay, so when is this stable? So when is this, in absolute value, less than or equal to 1? Well, how do we solve this? So the first thing is we can have r squared plus 2r plus 4 is less than or equal to 1, or we can have negative r squared plus 2r plus 4 is less than or equal to, or greater than or equal to, negative 1. Okay, so both of these are pretty easy to solve. So this goes to negative r squared plus 2r plus 3 is less than or equal to 0, which then goes to r squared minus 2r minus 3 is greater than 0, which then goes to just a quadratic equation. So it must add to 2, multiply to negative 3. So it's going to be r minus 3 and r plus 1. Yes, must be greater than 0, which then goes to r equals 3, or r equals -1. So the r equals 3. Cool. So that's our lower bound of our period 2 orbit being stable, which is what we expected, right? Because that's where our previous x steady state 2 actually bifurcated or became unstable. So now this will be to find our where our period 2 orbit becomes unstable. So again, this is negative r squared plus 2r plus 5 is greater than or equal to 0, which then goes to r squared, or I guess I could directly use the quadratic equation. So negative b plus or minus the square root of b squared minus, there'll be a plus from that, so plus 4 times a times c, so 4 times a, which is -1, times c, which is 5, so 4 times 5 is going to be 20, all over 2a, which is -2. So that goes to 1 plus or minus root 24 all over -2, which is equal to 1 plus or minus root 6. Cool. So 1 minus root 6 is less than 0, and r must be greater than 0, so that's not the one. So r equals 1 plus root 6 is where it bifurcates. Sweet. So let's grab this figure again up here. So we'll copy it back down. It'll be a little bit less messy now, or we can get rid of everything. So this line right here that I just erased is actually at 1 plus root 6. Sweet! So that is how you find out where your graph is going to bifurcate. So that's a pitchfork bifurcation. Again, it splits into 2, and then this is considered a different kind of bifurcation. I'm actually forgetting the name right now. A saddle point bifurcation, maybe, because the straight line stays unstable, but it is still a steady state. It's just an unstable steady state, and it bifurcates to a different period 1 orbit steady state, which is the same as a regular stable steady state. Cool. Again, we could just keep on going from here and here and here for all of these little bifurcations, right there, right there, right there. But it gets a little tedious, and it gets actually really hard to solve really fast, because right after this period 2 bifurcation, our quadratic or our polynomial becomes really high order, which becomes pretty difficult to solve even with computers. So now I actually want to characterize these bifurcations. So this is considered a tangential bifurcation, also known as a saddle node. And this is known as the pitchfork bifurcation. And that's because it looks like, a pitchfork. So, how do we know if something is, for instance, a pitchfork bifurcation? Well, in order to be a pitchfork bifurcation, it must have 3 properties. One being f of x, so f, the mapping, partial derivative with respect to the x parameter at x1, mu1 must equal -1. So in our case, mu1 is the r parameter, and then obviously x is x. And then it actually has 2 more conditions that it must satisfy. So f partial x partial mu plus 1/2 f of mu f partial x must not equal 0. And then we also must have 1/6 f triple prime of x plus 1/2 f double prime of x squared also must not equal 0. Okay, this one comes from a Schwartz derivative. So if you're interested, you can look that up a little bit more. I won't be going over it in this video. I just want to introduce that there is some criteria to tell you exactly what kind of bifurcation is occurring. And I'm just going to check and prove that the second bifurcation at r equals 3 is in fact a pitchfork bifurcation. So checking the first case, we have f of x is equal to partial over partial x of rx 1 minus x, which is equal to r 1 minus 2x. Okay, so plugging this in at r equals 3, x equals r minus 1 all over r. So that's going to be 3 times 1 minus 2, 3 minus 1 all over 3. So that's going to be equal to 3 minus 2 times 3 minus 1, which is equal to 3 minus 2 times 2, which is equal to -1. Yay, so it fulfills our first criteria. So second criteria, f of x of mu. So I already took my partial x, so now I can just take this. So this is equal to partial over partial mu, which in our case, mu is actually equal to r. Partial r of r 1 minus 2x, which is just equal to 1 minus 2x. And then we have f of mu equals partial over partial r. So I can probably write this as partial r of rx 1 minus x. Again, we can solve that nice and easy. X 1 minus x. Hopefully you guys have multivariable calculus, or else this is kind of hard to understand. If you want, you can look up partial derivatives to understand, but I won't be going over that in this video because I'm kind of short on time. And then x of x is equal to partial over partial x of r 1 minus 2x, which is equal to -2r. Okay, so plugging all these in at our points of interest, at r equals 3, x equals r minus 1 all over r. So we have f x mu is equal to 1 minus 2x, so 2, 3 minus 1 all over 3. F of r is equal to 3 minus 1 all over 3, 1 minus 3 minus 1 all over 3, and f of x is equal to minus 6. Cool. So plugging all these in to equation 2, we get 1 minus 4 over 6 plus 1/2 times the group. Let's see, this is going to be 2/3, 1 minus 2/3, and then times -6. So basically, we only have to compute this. If it's positive, then we have a -6 right here, and then this is definitely not equal to 0. So if we have this, so this 1/2 and that cancel out. So we're at 1 minus 2/3 is going to be 1/3. So this is going to be plus 1/9 minus 4/6, 1 minus, and then this is times minus 6. So this is equal to 1 minus 4/6 minus 6/9, which is not equal to 0. Cool, so our second condition is satisfied. Third and last condition, we need to find 1/6 f of triple prime. So we know f of double prime is equal to negative 2r, so that partial x is actually going to be equal to 0. And then we need to find x double prime. So f of x is equal to the negative 2r. So then we have 1/6 times 0 plus 1/2 negative 2 times 3, right? Because r is equal to 3. All this squared. And that, again, is not equal to 0. So, therefore, all three conditions are satisfied. And our bifurcation at r equals 3 is a pitchfork. Yay! Cool. So since I want to get into another two more topics, I'm just going to leave the r equals 1 as an exercise to the listener. So check to make sure that the r equals 1 does not fulfill these three criteria right here. So the first bonus topic, quote unquote, that we're going to be going over is the Sharkovskii's theorem. So the reason I'm going over this is because I won't be going over a proof because it's kind of hard, don't have time for that. A lot of people aren't interested in direct proofs, but basically it's a really cool theorem that's easy to understand. So it says that period 3 is greater than period 5 is greater than period 7, ... which is greater than period 3 times 2, which is greater than period 5 times 2, which is greater than ... period n plus 1, 2n minus 1 times 2, which is greater than period 3 times 2 squared, which is greater than period 5 times 2 squared, ... And then this period goes on period 3 to the 2 to the n, ... all the way down until you get period 2n is greater than period 2n minus 1 greater than ... period, let's go 16, period 8, period 4, period 2, period 1. So basically all that this really interesting theorem is saying is that if there's a period 3 orbit present, there's also every other period orbit possible. So that means that if there's a period 3 orbit, you actually have a period 5 orbit, you have a period 7 orbit, you have a period 23 orbit, any other number orbit, you actually have it present. It is probably, or it could be unstable, but it is present. So somehow if you hit exactly on one of these unstable points in the periods, you would actually see that period. So it's really powerful, and it actually is one of the things that introduces chaos, or is a characteristic of chaos. So if we copy this down again, and we look right in this region right here, this is actually one of the areas that is a period 3 orbit, this little band right here. And that's really cool because that means that right before that, this area is chaotic, or it's considered chaotic. And kind of thinking about that is a period 3 orbit can imply chaos. So that's a cool intro to Sharkovskii's theorem. Again, I'm almost just stating it so you guys can look it up. And the last thing I wanted to talk about is the Lyapunov exponent. So basically the Lyapunov exponent, probably butchered that spelling, is a measure of chaos again. So if your Lyapunov exponent, I'll just say it, L exponent, is greater than 0, then you have chaos. And that's really cool. So basically it's a measure of how different each iteration changes. So it's lambda, and it's approximately equal to the sum of natural log of absolute value of your xi's as I equals 1 to infinite n. Let's say that you do n iterations and you measure each xi for each iteration and you sum up the logs of these, and then you normalize by however many iterations you do. The exact Lyapunov exponent is equal to the limit as n approaches infinity of 1 over n sum natural log of the absolute value of your xi's. So what's really cool is, again, you can do a plot of this, which I will show you next. And anytime it crosses the barrier of 1, you get chaos. As we see from the image above, the Lyapunov exponent is below 0 until a R value of around 3.5. This is also where the plot above starts to exhibit a more erratic behavior, almost bordering on chaotic, as I would say. However, the Lyapunov exponent does drop below 0 again in the period 3 band that's located at an R value of around 3.85. So this is really cool, and it is just another example of how a Lyapunov exponent can characterize how chaotic a system is. Awesome. So I hope you guys liked this video. I know it was a really long video. Maybe I should have split it up into 2 parts to go over the more advanced topics after the more beginning topics, but I figured one video to spark interest is kind of cool. And if you're really interested, you could watch all 40 minutes. If not, you could just watch part of the video. I hope to see you guys next time, and thank you so much to 3B1B for hosting the Someone math exhibit this summer. Thanks. Bye.